Hey everybody, this is David from Dashboard. I have here also Ben from Theodo and Alex from Theodo, and today we will be co-hosting a webinar between Theodo and Dashboard, and we'll be talking about serverless and using observability at scale in serverless environments, and kind of how to think about certain areas in operational excellence and kind of operating serverless applications at scale, and what we have learned over the years, what we've seen different companies in the market struggling with, and what are the common challenges and how to overcome them. The first talk will be given by Ben and Alex, and you're also free to submit questions at any given time, and we will answer them either at the end of our talks or at the end of this webinar. So as soon as they make sense, we will give you an answer. This will also be recorded, so you can look at this at any time in the future as well. And hope you enjoy it. Feel free to give feedback as well. We're happy to make changes for the future. So Ben, I think over to you and your presentation.
Sure, thanks so much. Is my presentation showing? Perfect. Thanks everyone for joining. As Tavi mentioned, my name is Ben. I'm also joined by Alex. We both work at Theodo, where we help other people build digital products, normally using serverless. We both also help run the Serverless London meetup, which is actually happening tomorrow, so feel free to join. We've got some good speakers lined up. And we also run the Serverless Transformation blog, podcast, and newsletter. So if you're interested in serverless, feel free to subscribe to some of that content. And if you're interested in what we do at Theodo, feel free to go to theodo.co.uk/expert/serverless. In terms of our talk, I'm going to give a quick introduction to serverless as a whole, just because it's always good to get on the same sort of mindset of what serverless is before we go into how we're going to optimize it. Alex is then going to talk about optimizing serverless during development and when we're building applications. And I'm going to talk about how we use serverless observability at the sort of load testing part of an application's lifecycle. So what is serverless? Well, it's an architectural movement. It allows us to build and run applications without thinking about the underlying servers. It allows developers to send application code that's then run in isolated, abstracted containers away from the developer. And containers are probably a bad word to use. We send code and it's run, and we don't even care about how it's being run. And it's also the leveraging of third-party services to manage things like back-end logic and states. Now, there is a framework with the same name, the Serverless Framework, which is a really great infrastructure as code solution. We're not just going to be talking about serverless, the framework here. We're going to be talking about serverless, the architectural movement, and how these architectures scale. Why do people take a serverless approach to building architectures? Well, first of all, there's a cost reduction. It generally costs less to run our architectures in a serverless way when we just look at the exact billing, but also there's a massive reduction in the total cost of ownership. There's a lot less operations work that's needed. It's not no ops. There's definitely still some operations, but our operations resources are less focused on just running the application and instead can do things like optimizing it. And overall, there's a reduction in the total cost of ownership of running that application for the future. Developers, as they're focused less on running that infrastructure and the code around that infrastructure, they can focus on delivering business value and writing the custom code that embodies your business and its value to your customers. It's scalable from day one, and that's for startups where they have very low usage all the way through to companies that need to scale massively. Alex is going to talk about a couple of examples there. And also, as we start to make better use of the servers in our data center through a serverless approach, there are some theories that will be able to reduce the energy consumption of cloud and hopefully have a greener cloud infrastructure. It's not just Lambda. We're going to talk a lot about Lambda in our talk today, but I think it's often a misconception that serverless is just Lambda. Lambda is the compute part, the function as a service. It's almost sort of the poster child for service at this point. But there's also S3 for storage, DynamoDB is a NoSQL serverless database, API gateway for forwarding requests through to different services, Cognito for identity as a service in a completely serverless way, SQS for queuing, step functions for workflows, EventBridge for connecting event-driven architectures and third-party SaaS. There's loads of different services in AWS that are serverless, and you can build quite complex and quite advanced architectures by combining these in different ways. This does mean, though, that we need to combine them in ways that are scalable, and we need to be aware of where different scalability bottlenecks could be. I'm going to hand over now to Alex, who's going to talk about optimizing Lambdas during development, and then I'm going to, after that, talk about how we load test the architectures that result from development.
Thanks for the intro, Ben. So like Ben said earlier, I work at Theodo. I'm a cloud architect at Theodo. So I spend a lot of time with clients, helping them design and develop serverless applications. And with that, that means we use Lambda quite a lot. And clients are always concerned about getting the best bang for their buck, making sure their Lambdas run very fast and run as cheap as possible. So we're going to go over, in my part of the talk, different ways that you can do that. And we're obviously not going to be able to cover every single way possible, but just the sort of best practices and most common examples that you can use on your system. So to start, similar, I just want to go over what's actually involved when you run a Lambda. So starting from the very basics, it will download your code, start up a micro virtual machine, and then start bootstrapping a runtime, and then actually run the code that you've written to run in your Lambda, the part that you usually are concerned with. And there's like a shared responsibility model on who owns the optimization of each part. Downloading the code and running the VM falls onto AWS's side, and there's not really much you can do there. But you do have a lot of control over the runtime and your own code. Now that might sound like a bad thing. You only control part of the model, but it does mean that you actually get a lot of improvements for free over time. So there's a really good article by a guy called Nathan. I've linked at the bottom of the slide, and we'll share the slides at the end if you're interested in going to the article, who did some research back at the end of 2019 and showed that in just a year's time between 2018 and 2019, particularly for the node runtime, AWS was able to reduce that cold start time on their end by about 4 times, so about a quarter of the time that it previously took. And obviously we're in 2021 now. It's been a few years since then, so it's even better than it was back in 2019. But it's good to say that AWS will improve things for you over time. But what can you do today? There's kind of 3 areas that you can focus on, and we're going to briefly touch on each of them. First, you can do a bit to reduce the cold starts on your time. So if I go back a couple of slides, you can see when you hit a partial cold start, or the cold start that you're responsible for is the setting up or the bootstrapping of the runtime. You can also then power tune your Lambdas. So a lot of people just use the default settings that their Lambdas come with, but there are options about increasing memory, CPU, that we'll look at, and how you can pick the best values for that. And then lastly, there are some like code or architectural decisions you can make to optimize your Lambdas. It is possible to write inefficient code. That means the Lambda will take longer, and there's some simple best practices you can follow to make sure you don't fall into those pitfalls. So first up with cold starts, just in case anyone doesn't know what cold starts are, the first time you run a Lambda after a while, or when you're scaling up and you don't have enough Lambdas already provisioned, AWS has to go through that full process I talked about earlier to provision one for you, and that can take time. Now, as you saw, it's like 200 microseconds sometimes, or 100 microseconds. It's not the longest time in the world, so people often get a bit more concerned than they should, but it does add a bit of time and a bit of latency to your requests. And there are ways you can make that faster. So when we're talking about improving cold starts, it really falls into 2 categories. You can reduce the frequency that you experience a cold start. So depending on the type of application you have, the amount of traffic you have, what scale you're working at, your users might experience cold starts quite regularly, or they may almost never experience cold starts. And you can also work on the duration that the cold start takes. So how long, when you do hit a cold start, does it take to warm up that Lambda? Focusing on frequency first, it's actually not that common in a lot of use cases to actually hit a cold start. So here's a tweet from James Beswick saying that less than 1% of Lambda invocations actually experience cold starts. Now, what situations could you be in where you would experience more often? If you've got quite spiky traffic, so say you're a food delivery company, around lunchtime and around dinner time, you're going to have a lot of traffic, but then in the middle of the day, not as much, or in the middle of the night, not as many people would be ordering food. And so a lot of your users might hit that cold start as you're scaling upwards, and that's something to keep in mind. But if you've got more uniform traffic throughout the day, you're not going to experience them too often. If you do experience them, the only real tool you have is something called provision concurrency, where you can say you want to have a number of Lambdas already running. And so they'll be pre-warmed, ready for users for when users make requests. There are some plugins that you can use for different IAC providers, like the serverless framework, that try and manually hit the Lambda every now and then to keep them warm, but they're not as effective. Provision concurrency is really the way to do this, but it shouldn't be a default. Think about your use case. Look at the data. Do you actually need, are your users actually experience cold starts too often? And if they are, is it affecting their experience? Because otherwise you'll just be paying to have Lambdas ready at all times and not actually need them. What about duration? This is where we actually do have quite a bit of control, and it's fairly simple to keep the duration lower as possible. You just need to follow some key rules. When talking about reducing duration, you probably want to know how long the initialization is actually taking. A very simple way you can do this is with X-Ray, and it's quite easy to set up, but there are more powerful observability tools such as Dashper that will give you, say, average cold starts over the course of a day or a week or however long you want to look, instead of just looking at it function by function. Once you've looked, you see that cold starts are happening, they're impacting your user, and you think you can lower them. You've got a few things you can play with. So there's the package size that you've deployed. There's the runtime you choose to use. So you can use quite a different set of runtimes, with Node and Python probably being the most common, but you hear about people using Java, Go, or my colleague Ben actually used a custom PHP runtime a while back.
So anybody ever does that, but yes.
Also, the amount of code that you are deploying can affect it, and also how much of that code does initialization work. So a few things you can do, reduce, to tackle the first one, say package size. You can make sure your functions aren't monolithic, that you're breaking them down into small sub-functions that only do one thing. You can have a good bundling process that minifies the code and does tree shaking through things like Webpack. And you can make sure you optimize your imports. So, for example, the AWS SDK, you're probably not using the entire SDK. So if your Lambda just hits Dynamo, you can import just the Dynamo part of that. And if you do keep multiple handlers in one function, you can lazy load dependencies, because if you load everything at the top, you may have functions that are being slowed down by dependencies they're not even using. They're the main ways you can reduce cold starts, and it's quite effective. But another really quick way you can get a bit of extra speed out of your Lambdas is to enable HTTP Keep Live. With Lambdas, they set up TCP connections for every single request. And so say you're doing a few DynamoDB operations, setting that up each time can actually take longer than the Dynamo request itself. And so a statistic I was able to find online is that it's quite common to reduce these Dynamo operations from 30 milliseconds down to 10 milliseconds. And it is absolutely the easiest thing to set up. You just pass in an environment variable with the value 1, and you're good to go. I think the reason this isn't supported by default is because old versions of Node weren't able to support this feature. But yeah, it's a very quick win, and it does speed up the performance quite a lot. The next topic is power tuning. So a common misconception is to do with increasing memory when you know that your Lambda doesn't actually need much RAM. Well, memory actually leads to increasing the whole power of the Lambda. So stuff like the CPU, the network bandwidth, all get increased as you do increase that memory. And so this means that that by increasing the CPU, even if you don't need it, you can actually get quite substantial savings in time or cost. And so there's a really powerful tool called the AWS Lambda Power Tuning library by Alex's GitHub. You can look at the URL I've put at the bottom, but it's basically a state machine, a step function that runs your Lambda a number of times with a bunch of different settings passed through it, collects that data and sends it back to you in a really easy to understand format. It's data driven, and it shows cost and performance optimizations. You can actually pass in whether you want to just get the cheapest, just get the most performant, or if you want some sort of balanced middle ground between the two, it's available on the AWS Serverless Application Repository app, and you can integrate it with CI/CD. So, for example, every time you deployed, you could have it rerun this test to see what the optimal values are and have it change with each deployment.
We have some projects doing that. We don't actually let it make the change, but we just send a message on Slack, and then an engineer goes and looks and does the optimization based off the data.
Yeah, it's quite often recommended to have it basically make these auto change in development, but not in production, because you want a bit more control over production. You don't want things randomly changing. But as far as actually using this tool, it's super simple. You pass in an input with the Lambda ARN. You put in the power values that you want to try and the number of tries that you want it to do, and a payload. In this simple example, that's a Lambda that doesn't need a payload, but in most cases, you'd probably be passing a payload back, and it spits out some results for you. So it gives the recommended power, the cost associated with that selection, and the duration that it took to run. The really cool feature, though, is this visualization tag at the bottom. So you get a URL that if you go to this, you'll see a graph that shows over the different power values, how much it costs and how much your performance changed. So I think if I go to the next slide, I've got an example here of a CPU bound Lambda function. And you can see as we've increased the power, the costs are actually staying fairly flat and dipping. It's because as we've increased the power, the Lambda is actually taking less time to run. And so that means it's been cheaper. And then you'll often see this part where you then hit an inflection point, the performance is flattening out, so the cost starts to go up without you seeing it running much faster. This is a quite common sort of shape for a CPU bound example, but say you had more of an IO bound Lambda, you would usually see the execution being a lot flatter. So as the power increased, the execution time not really changing. You might get a small increase at the start because the network bandwidth increases with CPU, with memory as well. So say you're doing a Lambda, a call to Dynamo, that might be slightly quicker at the start, but then flatten out, but your cost raising up. So in that case, there wouldn't be much value in going to too much power. But for a CPU case like this, it's quite useful. So that's the power tuning part. I'm now going to focus on the architecture code side. So for this, you want to use an observability tool to understand how long different parts of your system are actually taking. Again, you could just use X-Ray, but using a fully fledged observability tool here is going to give you a lot more insights. X-Ray is always getting better, though. It's recently started to support EventBridge. So it is a good option to start with if you're still selecting a provider, but I would recommend getting one of those more powerful tools. Once you have seen which parts are taking too long, there's a few common areas that, or a few common mistakes that people make. The first one is fetching more data than you need. An example of this would be, say, doing a DynamoDB call to fetch everything with the same partition key, but then doing the filtering within the Lambda. This is going to mean you're doing a lot of processing in the Lambda that could have been done on the Dynamo side, and so that's going to lead to it taking longer, having longer execution times. There's also not using the related services surrounding Lambda particularly well. So kind of similar to the example I just gave, if you're doing scans in your Dynamo table, so it takes quite a bit of time compared to having like a good index, that will slow down your Lambda because they'll have to wait for that, and you're paying for that time. And there's also the defaulting to synchronous execution. A lot of developers, when they first move to serverless applications, aren't used to more event-driven or asynchronous architectures, and so they have everything wait to complete. And that means that your original Lambda that's doing this orchestration of the different pieces has a lot of like idle time where it's just waiting for other things to happen. And you might not even care about the results of those things that you've orchestrated. It might not be relevant for what you return to the user. You just need to make sure it happened. So moving to a more asynchronous or event-driven architecture will improve that as well and make them cheaper. So we'll start by looking at moving to async. When you've got a synchronous, when when you are doing your Lambdas in a synchronous way, you pay while your Lambda waits. If anything happens downstream that slows it down or causes problems, that original Lambda has to wait while that happens. And it also means you need to write custom code for error handling or retries. Whereas if you move to async and use events or queue services, you minimize the cost of waiting, because once you fire that event or you add it to a queue, the Lambda can return saying that it's done its job. With the queues, you can separate the fast and slow processes. So it might be very fast to receive a user's order, but then actually processing the order takes a long time. You can just put that order onto a queue and return saying that it's been processed. You don't need to wait for that actual order processing process to go on. It also means you get to lean on these managed services that have built-in scalability and reliability features, so you don't need to handle errors and retries yourself. They have built-in functionality to do that. The next thing is you don't always need a Lambda. Like Ben said earlier when talking about this serverless movement, people do see Lambda as like the be-all, end-all, and often don't look into other options. So for example, with orchestration, step functions might be a better choice, and it will avoid you paying for idle time. Or if you find that you're really just using Lambdas to transport data between places, say you're hitting API gateway, the Lambda is accessing Dynamo and then returning the values straight away, you could actually use a more simple scripting language like VTL that will allow you to operate directly on Dynamo, and you can skip the Lambda altogether. With AppSync becoming quite popular, VTL is seeing a lot of the spotlight at the moment, but you can do that with REST APIs and API Gateway as well. But I guess the last thing is making sure the code on the Lambda actually runs efficiently. So if you can parallelize your execution, that can speed up your Lambda times quite significantly. And I think I've put reInvent here. I think it was probably pre-invent 2020. AVX2 was announced, and this allows for, if you're doing any algorithms that on vectorizable data, you can do multiple calculations on a single CPU cycle. So you can speed that up quite quickly. If you're doing stuff with like SciPy and NumPy with Python, for example, this will get you some really good speed gains. So staying on top of these announcements and new ways you can leverage different services and different options, there'll be ways you can speed up pre-existing code. But I guess the last thing I want to say before I hand back to Ben is, you all know the famous quote of premature optimization is the root of all evil. Most of the time, you're probably spending more dev hours optimizing these things than they would actually cost in production. So you do need to lean on your observability to actually identify when you need to optimize and not do it until you can show the value. But for that 3%, you do want to know how you can go about optimization. So a bit of a recap on what we've talked about. Cold starts are getting faster just because AWS is doing a lot of the work for us. But we can change quite a few things. Mostly keep your packages small, use a bundler like Webpack to do tree shaking and minification for you, and only include, when you're accessing dependencies, be specific about what part of the package you need. Don't just don't just use the entire AWS SDK, just import the Dynamo part directly, for example. When power tuning, remember that memory equals power for Lambdas, and make use of tools that will automatically select the best options for you. And keep in mind, sometimes cost is important, sometimes speed is important. Don't make things faster just because it looks good on a metric or a slide in a ceremony. Always think about the impact for the user. Does it need to be faster? Or maybe this is actually a good time to save some cost. Also, with millisecond billing being announced in reInvent 2020, I think people are almost going to worry too much about the cost side. A lot of this is premature optimization. You will spend more time on developing than you'll actually save with some of the micro tuning. And the last one is, do always think about your architecture and your code. If you can do it asynchronously, that will save you a lot of idle time. And do think, do you need a Lambda for what you're trying to achieve? Using VTL, while not as nice as using your favorite programming language and runtime, will save you from hitting cold starts altogether, and also can be quite a bit cheaper. But that's it from me. So I'll pass back to Ben to talk about load testing.
Alex, if you don't mind, before we go, we do have a question as well.
Yeah, of course.
From the audience about Synchronous Express workflows. So have you had the chance to use Synchronous Express workflows with your customers? And do you have any recommendations around this for microservices / orchestration?
I can probably actually jump in, Alex. So, I've had a bit of experience with one of our customers, unless you have recently.
No, nothing recently. I was probably just going to mention using step functions to fan out and then fan back in, but you can probably take this.
From the parallelization side, definitely. I think I was just picking up on the fact it's a synchronous Express workflows.
Okay.
So the Express workflows are faster and cheaper, and we've seen that with some of our clients. There are some things that aren't available. So the wait state and step functions can be really useful. Obviously, in the Synchronous Express workflows, that's not possible. So when we can use Express, we are Express workflows, that is. And when we can't, we're not. But generally, we're trying to get a lot of our orchestration into step functions. It's a lot easier to fail over to the cloud provider and handle it that way than it is to have quite complicated Lambda functions doing these sort of workflows. I'm not sure, Bala, if that answers your question, but feel free to add any more onto that.
Awesome. Thank you. I'll let you go on.
Sorry for jumping in, Alex.
No, thank you.
Topic close to my heart. And just on Alex's point on parallelization, I think, as Alex said, we don't want to cost optimize for the sake of it and spend too much money. At the same time, quite a nice anecdote from one of our projects at the end of last year. It was a client who was doing PDF generation on Lambda, and we were helping them optimize different parts of it. And the Lambda function was starting to get to a really, really slow running state of, getting to that 15-minute mark where Lambda functions could time out, let alone the 30-second API gateway timeout. So there's already some queuing and some asynchronous front-end work. We split that using step functions into several different Lambda functions that fanned out. They all generated the sort of sub PDFs, and then one Lambda function pulled them from S3 and then merged them together, writing the end result to S3. And that reduced the time massively. Not only did that mean they're not being hit by the cold starts and they're making some cost optimization, but the user experience then meant that the time to generate PDF wasn't linear to the length of the PDF. And those PDFs were hundreds, if not thousands of pages long for this very particular industry where they needed these long audit PDFs. So parallelization is definitely a massive part there. I'll jump off to the load testing part and we can jump into, actually another question's just come in. Have we had a chance to test the new features bootstrapped with Docker? I'll speak for myself and then Alex, if you've got anything to add on. We have been looking at the container support for Lambda. Personally, I and we are still sticking with doing Lambdas the more traditional way. We think we can really have quite a slimmed down package that we're working with, and we have the skill set around that. I think the Docker support is great for accessibility, people moving into serverless. I think there's going to be a lot of people trying to lift and shift applications into Dockerized Lambda, and that's really not going to end too well for them unless they happen to have written their architecture in a completely stateless, event-driven way. And even then, I think there's going to be problems. So I still think writing Lambdas in the traditional way, which feels weird, is probably the route to go. But I think Docker is a massive enabler to bring people into serverless who might not have felt it was accessible before. Alex, I don't know if you've got anything to add there.
Completely agree with you there, Ben. On the projects I've been on since it was announced and supported, I've not had a use case yet, but I do think it will provide a lot of people a pathway into serverless, where before they were worried about losing their tooling or were a bit too intimidated. It does increase that accessibility. As far as latency, I've heard some people talking about it being a bit slower, but I've got no experience on my end.
Yeah, looking at the stats that they publish, it seems like they've done incredible work to get it fast. I've not done any research myself. And then API gateway alternative because of the 30-second timeouts. I think it's important to think about why you want a network request to take longer than 30 seconds. So we would often have some front-end queuing. A lot of the time when we're sort of building quite complex single-page applications, let's say an admin system managing PDFs that are generated as a result of a sales process, we're using services like AppSync to have a WebSocket connection between the front end and the back end, and that's getting updated when the result comes out. So I think you need to change to an asynchronous flow between your front end and your back end. And of course, you can have Lambdas triggered by writes to S3. So let's say you generated a PDF, it triggers a Lambda function. If you're using API Gateway WebSockets, then you could go trigger the right socket there. Otherwise, we're using AppSync a lot to sort of manage our workflows around long-running tasks. Alex, I don't know if you wanted to add on to that.
No, not really. I think Ryan's brought up a similar question based off what you've said. In the case of informing the front end about asynchronous events in a microservice architecture, do you perform long polling or WebSockets? In my current project that I'm working on, Ben briefly mentioned AppSync there. We're using the subscription architecture that AWS has in AppSync. So that really hides a lot of the WebSocket stuff for you, but it provides that WebSocket connection. And you just do things in the GraphQL way, and it kind of just magically works. It's really powerful and high level compared to doing it yourself with API Gateway.
WebSockets as well are quite approachable. You do need to maintain sort of a list of which connection IDs to which people. It doesn't have things like a broadcast facility that you can achieve with AppSync, which is a lot of the reason people go down the AppSync route. But yeah, we're generally doing, even if we're not using AppSync, API Gateway WebSockets to do that sort of communication. We actually written an article. It's on the serverless transformation blog. It's serverless-transformation.co.uk. I'm sure there'll be a link at the end of my slides. But we've written a comparison of the different approaches for that, Ryan. So from polling to long polling to WebSockets. And yeah, most of our architectures, when we're starting to get to those issues, it's already quite a complex application with lots of sort of lifecycle events happening between the backend and the front end anyway. So we already have access to a nice WebSocket platform. If it was just a one-off thing that you needed to have that asynchronous event, then yeah, polling isn't always the end of the world. Dealing with WebSockets is its own complexity, but generally we're using WebSockets at this point. I'll jump into the load testing part of this, but feel free to keep dropping questions in, and when we get to the end of this section, we can go through them. So Alex has done a great job going through Lambda. When we're developing it, how do we optimize Lambda? As I said at the start of the talk, let me just change to the right place. There we go. Lambdas don't just live on their own. There's lots of other serverless services. We're generally building 100% serverless first architectures, so no service involved at all, completely serverless services, composing them into microservices and sometimes involving things like EventBridge to handle the communication between those microservices. When it comes to optimizing even Lambda, we need to make sure we're looking at the application holistically. We need to make sure we can understand where the different bottlenecks can be, how serverless scales differently, and how our Lambda code might be impacted by that. So how does serverless scale differently? Well, as I said at the start, it's great. Serverless is pay per use. It means it's really good for startups as well as large companies. And it's a different model in terms of how we think about the financials. It is massively scalable. That can sometimes be a problem. Denial of wallet is a new term that's really emerged with the move to cloud and serverless. And that's not a denial of service, but it's a denial of wallet. Someone's requesting so much against your system, which is nicely scaling as you wanted it to, but you're paying for all that scalability, and that can get quite expensive and can be a way that your application gets shut off. There are AWS service limits. There are those soft limits that are there for your protection, to protect you from accidentally spending hundreds of thousands on Kinesis. There are soft limits on every service to try and have a sort of soft limit that you can raise if you want to and gradually increase that with your scalability. There are also some hard limits. They change between sort of using limits and quotas, but there are some hard limits of just, this is as scalable as this particular service goes. If you're hitting those, you probably get some quite high scalability, or maybe there are some anti-patterns in your architecture you're going to have to work on. But it's not the end of the world if you start to hit hard limits. You just need to have mechanisms around that so your application can deal with it when you start to hit those high limits. You can outpace non-serverless components. It's nice to say that we build serverless first all the time. It's definitely not all the time. There are times where there's a legacy existing relational database that we're interfacing with, or other microservices that we're interfacing with that we might actually scale faster than. And we don't want to particularly outpace, sorry, I think my slides just disappeared. We don't particularly want to outpace the non-serverless components of our architecture. There might be other teams in our company. There might be other applications that we maintain. They might be third-party services that we're interacting with. And when we scale massively faster than them, we can actually start to denial of service those services. So we want to be sort of a good citizen in our architecture, not attack the other components, but make sure we have good systems around them to know not to hit them too hard, and also to back off when systems are struggling. As Alex mentioned, cold starts can impact, especially when there are sudden spikes. And as we start to combine multiple services in a more distributed architecture, those bottlenecks are kind of harder to spot. When you have an architecture diagram with one big box and then a database, well, there aren't many places where the bottleneck can happen. When you have these more distributed architectures, and I'm going to show you a real-world example of in a minute, it can be more difficult to spot those different bottlenecks, and that's where observability is a massive enabler. And finally, regional distribution of traffic. As we have obviously different AWS regions running our architecture, when we start to talk about global scalability, where's our traffic coming from, which regions it's hitting, how are we syncing data between them are all considerations. We had one client about 6 months ago using Lambda Edge for a really nice piece of authentication work, and it looked up in DynamoDB a particular entry, and then it would make decisions about where the person was routed to. That was great. They were using Lambda Edge. It was super scalable. But when they started to spread to different regions, even though they were deploying in those regions, the Lambda Edge was hard-coded back to the London region. So somebody in Tokyo was hitting a Lambda Edge destination. That was then calling all the way over to UK to get some data from DynamoDB, and that was going all the way over and back. So we also need to think about how geographic distribution, as it's becoming easy for us to distribute geographically, can impact the scalability of our application. So this is where load testing comes in. Again, like serverless, it's one of those terms that means different things to different people. For me, it's simulating different concurrent traffic levels on an application to validate its scalability. There are typically two types of load testing. So there's protocol-based and browser-based. Protocol-based hitting the direct API, typically over an HTTP protocol. Browser-based would be spinning up actual browsers and then mimicking user interactions to then go on and trigger realistic protocol-level requests. Typically, when it comes to serverless, we're testing really quite high scalability, and therefore protocol-level testing is what's best, because it would be far too expensive to spin up that many browsers for simulated testing. And typically these systems have quite clear protocols that we can work around. Just one point though, those protocols, they could be HTTP API requests, but they can also be more custom. We have an application at the moment that's a completely event-bridge driven application, actually has no front end that users are interacting with. It's more of a system that's fitting into a number of other microservices of an existing global architecture. We're load testing that with an adapter we've written that enables us just directly inject events into the event bridge rather than going through the latency of API gateway and Lambda and setting up particular infrastructure just for that load test. So what are the components of a good load test when it comes to trying to make sure application can scale and finding optimization points? Well, we want to be running against an exact replica of the production architecture. We want to have observability tooling in place, tools like Dashbird. We want to have repeatable scenarios that we can really conduct these as scientific experiments. We know the answer we're expecting to get out, we can repeat it, we can make changes, and we can really test assumptions about our scalability. We want to have realistic flows. We want to actually test the paths users would actually go down rather than just, we're only hitting this one Lambda, and now we're saying our system is scalable. And we want our traffic to have geographic distribution to catch those problems I talked about just a moment ago. To get a bit less theoretical and talk about a real world application that we've built, but also then gone on and done the load testing and seen it grow. Gamercraft are a really cool company in the esports space. They try to enable amateur gamers to compete in tournaments. So it's all about building good teams for different esports games and building the leaderboards and tournament components around that. So they obviously needed a platform that could support quite a high volume of users, accommodate traffic spikes when these large tournaments were happening, but also accommodate periods of low usage without spending a lot of money. So their architecture is composed of a number of different microservices, which came from the result of some domain-driven design workshops. One of them is a tournament microservice, and then that interacts using EventBridge to a number of different services like notification, user, match, team, and prize. If we just drill into one of these services, this is a tournament service. It's probably a little bit small on the screen, but you can see there's a lot of Lambda there. There's also a lot of other services, and these Lambdas are integrating through EventBridge, through step functions, and there are some quite distributed paths that are occurring in the architecture. This can make it quite difficult for us to validate a number of questions that we want to test. We want to validate that our cost estimates are correct as our load increases, because we don't want to overspend when we can't afford it. We want to make sure that we identify any service limits that we need to raise, so that we can do that before we go to production and have issues in production. We want to identify any limits that are hard and that we can't necessarily raise, but we need to change our architecture to work around, or maybe limit our users at peak periods. We want to identify any third-party services, particularly the non-serverless ones that we need to protect from spikes. And we need to identify any bottlenecks to scalability and the impact of regional distribution. And this will help us identify bottlenecks, but also opportunities for optimization. So that's quite a lot to do. Where do we start? Well, first of all, it's the environment to test against. I'm a big proponent of sort of isomorphic ephemeral load testing. So having an exact copy of the architecture, we can just spin it for a load test, run the load test against it, and then throw it away. We actually do this for testing. So on our 100% serverless architecture projects, we use something called serverless flow. It's basically an adaptation of Git flow, where when we open a pull request, it spins up a complete architecture. We run the the integration tests against that architecture. We're then provided with a domain name where we can go run some functional testing, and then we throw that architecture away. This same approach is actually really useful for load testing. We can get an architecture that's exactly the same shape as production, spun up for our load test, isolated from any other factors, and then we can throw it away, spin up a new one, repeat the test. It's a really good way for us to have very sort of repeatable experiments and very isolated experiments. Secondly, we need some metrics, and this is where services like Datadog really come into play. There are some basic metrics. Response time, of course, is a key one when we're optimizing Lambda. Error rates and any throttling. These are the things we really need to look out for when it comes to potential issues the system are having and potential limits that might need to be raised. CloudWatch and X-Ray are your friends. These can be really useful to spot issues in production, but also spot metrics during our load testing. And Lambda Insights inside of CloudWatch is fairly new, and it has some really interesting insights in terms of Lambda cost, and memory usage can really come into play on some of the power tuning stuff that Alex was talking about. But those services are good, but typically when we come to load testing, we need to have some quite advanced dashboards around what we're doing to really drill into the key issues. Dashboard is, of course, an amazing serverless observability provider. It can give you access to all the metrics you need when running load tests, as well as in production, being able to spot issues as they arise. Now we've got our metrics, we need to actually run the load test. So we need some sort of toolkit for running that load test. Artillery is a really great tool for running load tests and smoke tests. It's been around for a long time. I'm a big fan of it. Developers and QA engineers tend to use it. To use it, and I'm just trying to find how to scroll through my code. Cool, there we go. To use it, you configure a file like this, where you have a number of phases. This can have an arrival rate and a duration. You can have different ramps up to sort of simulate a realistic flow of users being added to the site. You can have a payload, and this could be a CSV of sort of fuzzed keywords, or it could be using something like Faker to generate data on the fly. Then you have a number of scenarios that you're testing against, and then from localhost, you could just run artillery run, and then you give the path to this YAML file, and it will run the test for you. This is great, but when we start to get more scalable, it's going to outpace what my MacBook Pro can do, so we need to run it somewhere. As you're probably getting from this talk, I'm not the biggest fan of servers, so we need somewhere else to run it. And luckily, there is a service that can run code without us having to think about or manage the servers, and it has massive parallel scalability, and that's AWS Lambda. And even more luckily, there is serverless artillery, which combines serverless and artillery to get serverless artillery, which allows us to run our load tests in a completely serverless way. How does it work? Well, again, my computer's involved. I'm running that file, but it is then going off, creating a number of Lambda functions to orchestrate a load test using Lambda, and then shooting those requests off to the infrastructure under test. One really important point, run it from a different AWS account. We're trying to assess what our limits are going to be. If our load test is using a load of Lambda functions, we're going to hit our limit faster because our load testing is actually taking up some of our capacity in terms of Lambdas. So it's very important to run it from a different AWS account. It also can provide more realistic traffic paths, especially if you start to do some cross-regional testing. And it's also a nice isolation point. I wouldn't suggest running it against production. Again, spin up one of those isolated environments to test against. Treating load tests as experiments is something I mentioned a few times. All of these tests should be repeatable. So we should be committing a file about the context. So a quick README that's saying the context. This is a scenario template that we used, and these are the results. This allows us later on to come back and actually see if the changes we made affected the results. And it also enables us to spot potentially scalability takes a massive dive. What's changed since we ran our last test where the results were okay? And then we can go run a Git bisect and dig into the actual root cause for that scalability issue. So treating these load tests as experiments is a really crucial part in optimizing for the long term rather than just that particular week. So to go over it, the components of a good load test, it's against an exact replica of production. There's observability tooling like Dashbird in place. The scenarios are repeatable. We can simulate a really high scale. We have a realistic user flow. There's geographic distribution, and we're committing these tests to be completely repeatable. If we combine that environment that's completely isolated, the metrics coming from a tool like Dashbird and serverless artillery, that will provide you most information to know how well your serverless architecture is going to scale, but also identify areas for optimization using some of the techniques that Alex talked about. As we mentioned, we work at Theodo. We help people with serverless. If you're interested, feel free to reach out. All the slides here are available on Alex's slides.com account, and I'm sure we'll share these out afterwards. The article I mentioned earlier is on the serverless transformation Medium, so feel free to follow us there. Me and Alex sometimes tweet about serverless, so feel free to reach out. I guess if anyone has any questions before we move on to Tavi's talk, feel free to message them in the chat.
Sure. So I think we actually have another question. So what are the advantages of artillery over Gatling? Do you know a tool called Gatling?
Yeah, Gatling is a very similar tool. A bit like a Gatling gun, you point at your architecture and you can fire a load of load tests against it. When I was looking into it, which was a year and a half ago, I didn't find a good solution for sort of a serverless Gatling. At this point, Artillery have like a professional version that could be run for you. So in that sense, it is serverless. I don't know if Gatling have got there yet. But for ours, the main advantage for serverless is the fact that serverless Artillery allows us to run these from Lambda against our architecture. But yeah, Gatling is a very similar tool.
Awesome. So thank you. We don't have any other questions at the moment, but if they come up, we'll definitely take a look at the end as well.
Awesome.
Thank you, Ben and Alex. I guess it's my turn. So I hope you can see my screen. So I'm going to be talking about serverless observability and the best practices and common mistakes. Dashbird was already mentioned a lot of times today. I swear I'm not paying Ben or Alex anything, but we'll take a look at the broader kind of practices of observability and kind of the challenges that like I have come across personally and what we've seen among the Dashbird users over the years, and what are the biggest challenges people are struggling with and how to overcome them, basically. A quick intro to myself. I'm the CEO and co-founder of Dashbird. I've been a developer for over 14 years now. I started using serverless quite early on, so I've been playing around with it and building different solutions for over 5 years now. So at the very beginning, the community of serverless was quite early. We didn't have even the serverless framework or like any of the kind of good tools that we have now. So at the really early stages, life was quite different than it is now. Quick intro into Dashbird as well. We're one of the leading serverless monitoring platforms. We have thousands of daily users that are relying on our platform, and we help organizations by providing observability, alert automation, and well-architected reports, which we believe together enables an organization to build and scale their serverless applications. So why is it so hard? Why are there so many companies using, or like why are there so many companies doing the serverless observability part, and why are this space like with so many vendors? So we believe there's a lot of fundamental challenges that serverless kind of introduced, or actually the newer age of cloud and all of the managed services, the spectrum of different managed services. The first thing is application logic is highly distributed across many cloud resources. So a typical serverless environment that has any sort of scale, we're looking at hundreds of different functions, of different like API gateways, databases, queues, step functions, Kinesis streams, and that's a really large amount of data being produced, logs and metrics and traces, they're all distributed. And at that scale, it takes time to navigate, and developers can struggle to understand and comprehend the activities across such applications. Also, it's hard to comprehend on the user side, how are your users actually experiencing the system? Is there any failures? What's the latency across like your 100 API endpoints? And also, we've seen that failures are hard to notice. So when at my previous company, to be honest, a lot of the times we found out about failures when our customers told us that, hey, this part of the application isn't working. Admittedly, it was our fault, but this was a challenge for us every day. Another thing that's more recent, but we've seen a lot of companies also kind of working on, is maintaining the best practices and efficiency across the infrastructure, across the environment. And there's things like the well-architected framework that has done a lot, but it's still quite a difficult topic and a big challenge for a lot of teams. So this is kind of, to name some, the biggest challenges of this world in serverless. And kind of here we have just a typical serverless infrastructure, not even that much load or not even that much resources, but still you can kind of imagine each one of those items on the screen can actually fail. It can develop its own problems. It can cost you a lot of money. So there's risk involved, and there's time sink into understanding how it's working at any given time and how changes affect the system. So that's really kind of the first challenge that you go into, and it doesn't really even matter if it's like AWS or if it's some other environment. You're going to, like, the managed services always produce logs and metrics and traces. They don't have too much access to the code except functions, but you can't instrument your DynamoDB, unfortunately, or fortunately, or you can't kind of make code changes to your API gateways as well and attach an agent. So you're stuck with what is being outputted, and you have to make do with that. But yeah, if you imagine even 50 functions with like 1 million of executions, which isn't a big stack by any means, that means 350 metrics, 5 gigabytes of logs daily. Each one of them can contain meaningful information, and you have millions of X-ray traces as well. So this is what some of the users are facing on a daily basis. Quickly, before we go into kind of how to fix that and how to think about that, what does observability really mean? So the definition of observability is that you can measure the internal state of the system from the outside or the outputs of the system. So in theory, if we look at, like, for example, CloudWatch metrics and CloudWatch logs and X-ray traces, all of the data is already there. It's a matter of accessing it, interrogating it, analyzing it, and making it understandable for the engineers. So this is what we believe is the future, as a big difference from any of our competitors. We don't actually instrument any code, any functions. Dashboard takes 2 minutes to set up, and there's just one CloudFormation template that you deploy. So you don't touch your functions at any point. We only calculate the state of the system by looking at different outputs. And like, if we break this down even further, what kind of logs do you actually have, or what kind of different data points do you have to understand the inner state of the system? So, for example, in AWS, you're working with CloudWatch metrics, with logs, X-ray tracing, and then service maps from those traces. access logs, and you also have resource configurations. So you actually have a lot of data. If you kind of think about it, you can understand code exceptions from the logs. You can correlate that with traces. You can look at metrics and how changes to the configuration change the performance of your application, or you can calculate some costs from the metrics. There's also access logs. So actually, there's a lot of data already present in AWS. The problem is how to work with it in a meaningful way and how to reduce the time to like understand this data. So this is one of the main problems we've been working with, and I'm not going to go into a product pitch, but I think what's important is, if you think about all of that data, make that data somehow available to your developers in a better way. So try to offer them with solutions on how to break down the silos, so how to correlate logs and metrics and tracing data. So if you look at the specific execution, for example, or a function transaction, what was the actual tracing, or like the spans of that invocation? What kind of calls did it make to a database maybe, or to another function? What was the metric, what was the concurrency at that time? And like make it so that you can actually jump between those different data sources and silos and understand the big picture. The other thing is like in AWS, you have a lot of different metrics and like large amounts of data, which makes it hard to understand what's really important. And like the most important thing about your business is how your users are actually experiencing the application. So try to map out those specific metrics that the best kind of show how your users are experiencing it. So whether if it's API latency and the amount of API requests, or the delay of a data pipeline, or the amount of feature adoption, make sure those things are up on a dashboard and you have an ability to track them, and you develop an understanding of how those correlate. Another thing is basically a layer of abstraction. So if you look at a large-scale application, you should be able to have a view of the entire account. So how healthy are all of your microservices? Like have a score for how many requests are going through successfully, or how many problems you currently have that are critical. And overall, is there a cost spike perhaps, or a spike in latency or delay? So always kind of try to look at it from the most broader view to then divide it into, for example, microservices. So try to look at different logical business units or like logical parts of your applications separately to see how they perform, what's their health, what's their cost, and kind of how are those like changes that you're making affecting a specific feature of your application. And then if you're troubleshooting and debugging, you should be looking at resource and transaction level data as well, which helps you to actually optimize a single resource or understand one single activity in your application. So Dashboard admittedly does this, but there are other ways, there are other vendors, and there are ways to build this yourself as well. It is hard to build it yourself. In my experience, you could use something like Elasticsearch and combine it with some metric store and build alarms. It's a lot of work, and in our experience, it's not cheaper, but there are like different ways of doing this. But try to think of it in this way. So, for an example, this is a screenshot of our service where you can actually go from a service level to resource level to an actual down to one transaction and into the logs as well. So you can look at all of the layers. There's views for accounts and for services as well. So we kind of give you an end-to-end view across your system, and you are able to visualize different parts of your application. So that's challenge number one, is making sense of all of those big amounts of data, large amounts of data meaningfully, and not wasting time trying to understand it. The biggest, or the second challenge that we see in the market is guarding against a large variety of known and unknown failures and problems you might be coming into with your serverless environment. So the core problem is when you're using different serverless components like API gateways, functions, and databases, each one of those different services actually has a lot of different ways that they can have problems. Lambdas can have timeouts, code exceptions, they can run out of memory, they can have cold starts, or like hit the concurrency limit. API gateways can also time out or have latency issues. You can have integration failures or configure it wrongly. And the same goes for basically every service. So your SQS can fill up, your DynamoDBs can have all sorts of problems. So it's really kind of a twofold problem. First is identifying and mapping all of the possible failure scenarios. And the other is actually managing the alert coverage across those resources. So if you imagine having like 200 functions or like 200 resources, and you have to manage like 2 or 3 alarms for all of them, that's a lot of work. And if you're continuously changing it, then that's quite a lot of work, and not a lot of teams can do it at all times. So this is actually also, as a side note, in our user base, it's one of the biggest kind of values that we provide is enabling organizations to react to problems as quickly as possible, and then giving them the confidence to quickly iterate, to make deploys during all times of the day, and if something goes wrong, to quickly react and fix it. And that's really what you should be setting your goals against, is to reduce the mean time to discovery for anything that's affecting your customers, and raising the confidence inside the organization to quickly build and iterate, which minimizes risk, but also makes your team much more efficient and makes the organization much more competitive. Another side effect is that developers eventually get to focus on the customers and not on the operational stuff, not on managing alarms, and not having to learn every service end to end to be able to use it. Also, your alerting kind of strategies should allow you to learn from mistakes over time. So if you have incidents, you should document them, and you should have a continuous kind of guidelines and cadence of going over past incidents and learning from them. So define the expectations to your applications, and then start basically searching and filtering for signals in your monitoring data. So whether if it's logs or metrics, or kind of what's going on in the configuration of your resources, you should be running checks. You should be listening those signals and trying to like have coverage at all times to be able to react. So like what we do and what I recommend implementing in some way, this could also be done with some other tools. The first thing we do is we detect all of the meaningful events from logs. So whether you're using Node.js or Java or Python, or you run into a service-specific failure, such as a timeout or a configuration issue, we actually have a filter that catches that from the logs, and it extracts the stack trace and then connects the event with X-Ray, so you can actually see what really happened. Like, was it the database call that failed? Did your developer make a mistake? Is some downstream service taking too much time? And the kind of the good thing is that you're able to detect those things in real life, in real time, and then correlate the data. So logs and metrics and traces are or present in that specific failure event. The second part is metric alerting. So as we know, CloudWatch produces a lot of metrics for a lot of different resources. So when you're starting out to implement your alerting strategy, you should be looking at customer-facing metrics and indicators first. So API latency, failure rates, and overall health of the service. This enables you to catch most of the problems in a timely manner. So if you have an API gateway that has a function and then has 10 different functions behind that one function, then obviously you should use step functions or something else as well, but at least have an alert for that specific API endpoint so that if it fails, you will get an alarm, even if you're not going to cover all of your functions with alarms. And also look at leading indicators. So most of the problems you run into happen quite gradually. So your SQS queues are filling up over time because you have maybe too much or too little compute consuming it on the other hand. Or your API gateway latency starts increasing because something is piling up on the backend or something is being overloaded. Same goes with like memory usage and like other incidents. So this is a bit harder. There's different kind of ways to do that in CloudWatch. You can enable anomaly detection for some metrics, although this only works for things that machine learning can actually figure out. We also work on this at Dashboard, so we look at past usage and past activity, and then let you know if there's an anomaly in your API metrics, for example. Also, in alerting, one of the quite important thing in serverless is, as it's pay per use, you could monitor the cost of your services as well. So if you're mindful of that, if there's risk of cost increases, this has happened internally as well in Dashboard and in like different companies I have seen and I have worked with. So definitely you can set alarms in CloudWatch. Actually, in Dashboard, I don't think it's easy in CloudWatch, but there are some ways as well to set billing notifications. But I think one of the most important things is to do it programmatically and centralize it. So don't have some of your alarms in CloudWatch and some of them in Dashboard and some of them in Datadog, because that leads to trouble and you missing something at the end. But also there's a human factor. So most of the alarms, you do need to set a lot of alarms for serverless. So it's better to do it automatically and abstract that away. One of the services, obviously, that does that is us. So we equip you with pre-built checks for logs and for metrics, and continuously scan every piece of your infrastructure for any type of failure. So that includes detecting all of the things I just mentioned. Those checks are also publicly available, so you can have visibility into what's actually being monitored for. Now we arrive at the third challenge. So what we've seen with serverless is that the sheer amount of resources and complexity and kind of the new best practices and the ever-changing environments are quite hard to manage the posture and security. And there's like so many moving pieces and so much change happening and so much knowledge also in the community and like best practices you should be following. So that's kind of what we see companies struggling with as well. Some companies are using consultancies to order audits, which I think is a good practice to have like annual audits and like somebody from AWS going and having a look into your infrastructure and seeing if they can spot something that could be optimized. And yeah, you should be looking at the well-architected framework. It's a great resource for basically learning all of the different things around design thinking and security and reliability, and how do you actually optimize serverless applications. There's also a serverless lens, well-architected white paper, which I highly recommend. The problem with the framework and with kind of even knowing all of the having the knowledge around security and reliability is that there's tons of work to actually audit and to go through and to continuously monitor, and it's hard to transfer that knowledge across teams. So if you have 20 developers, each one of them has to know actually how to fix a security issue or detect a security issue in your functions. So this is also quite the challenge. There is a resource in AWS, the Well-Architected Labs, which enables you to go through and train yourself. It's free of charge, and it walks you through different disciplines of the well-architected framework. And this is a great resource to learn hands-on and get familiar with how to be well-architected. So as it happens or stands, this is also something that Dashboard can do as a product quite well. The reason is, as I mentioned before, we collect basically all of the available data about your service, so all of the logs, metrics, and configurations. So it's easy for us to continuously scan. Our application has over 80 checks that we continuously monitor against. And like common violations that we are seeing is abandoned resources. Let's say you have some old functions that you've deployed. Maybe they contain some packages that can have security risks. And this is something that has happened, is that functions get hijacked and used how they're not supposed to be used. And this is also true for like other resources as well. So you should be looking at abandoned resources if something hasn't been used. Also waste, over-provisioned resources or under-provisioned resources taking too much time to execute, like functions, is also a big thing. So we try to not waste money and resources. But also there's a lot of configurations for a lot of different services. So you can use continuous backups. You can use customer managed keys for your DynamoDB tables. You can enable logging and detailed monitoring for API gateways, payload encodings. So there's a lot of configuration opportunities that when you care about security and compliance, you should be using. Also, there's like more like informational insights like tagging and naming and complying to different kind of practices or kind of good guidelines. So this is again out of the box. This is I don't know another vendor. There are some tools in AWS that also scan your resources. There's also companies like Cloud Conformity. And some other security providers. So this is quite new, but yeah, this is what we see. The third kind of biggest challenge in the market. So kind of recap, your strategy for observability should be threefold. First is getting all of the data into one place so you can understand what's going on. You can look under the hood, you can understand the user's perspective, and you can really save developers time from debugging and troubleshooting. The second part is failure detection. So you should be aware of any problem in your application with like less than a minute, ideally with 10 seconds. And that's one of the biggest levers we've seen in monitoring, is if you're able to do that, then your customers are happy. So this is really really important for our customers. And the third part is manage the posture and security of your application. So don't enforce bad practices, be optimized, try to continuously look for ways to improve across the system. And that's it on my end as well. So
That was really cool to have you. I'd not seen the well-architected labs before. I'll have to give it a look.
Thank you. Yeah, it's a long-term work in progress. So I think we do have a couple of questions.
Yeah, I think one came in on the provision concurrency just at the end of the first talk.
Yeah, maybe you can take that.
Yeah, I mean, my answer is not going to be too amazing. We are using provision concurrency on projects, and it is a problem when you're dealing with these sort of versionings. If you're just using something like the serverless framework and you add a provision concurrency, that's fine. When you start to want to have different sort of concurrency policies, I forget the word, feature the versions, it gets difficult. You're right, aliases is a nicer way of dealing with it. But then if you change where the alias is pointing, it's going to change what it's configuring. And you can't have more than one alias pointing to the same thing. When we start to have routing configurations and aliases, it can get a bit weird. So it's still a bit of a messy area. But yeah, I think aliases is the best approach right now, Alex. I don't know.
Yeah.
Sorry, Alex, if you...
Yeah, aliases are pretty much recommended for this issue. The main thing you'll hit with aliases is when you deploy a new version, your cold starts will stop because it'll move to the new version straight away. And so the provision concurrency will stop. So you'll start hitting cold starts again. A suggestion to get around this, I've not tried it myself, is to do like a wait alias when you deploy the new version and slowly ramp up how many are hitting the new version as they warm, and that provision concurrency gets set up. But yeah, not tried it myself too much, to be honest.
Awesome. So I think there's one question for me as well. Will there be an integration with EventBridge as a partner event source? Yes, but we don't currently have it. So hopefully in the next couple of months, we'll be able to launch that, but not yet. So I think that's also the end of our questions. Thank you, Ben and Alex, so much for doing this. I really enjoyed listening to your talk. I think I learned a lot, hopefully the others as well. I'm sure they did. And I'm looking forward to doing another one with you.
Yeah, thanks so much for hosting us. Your talk was great as well. And the well-architected view that you're doing inside the tool, it's really exciting.
Thank you.
Yeah, right. Thank you very much, Tavi.
Thank you. All right. Thank you for listening, and tune in next time.
Thanks so much.
Thank you.
See you guys.